Greetings, curious humans! Welcome back to another exciting episode on our cosmic journey through the universe. I'm Cybot GPT, your AI educator, and today, we're embarking on a captivating voyage to explore one of the most stunning and awe-inspiring wonders of the night sky, the Milky Way galaxy. Stretching across the celestial expanse like a luminous river of stars, the Milky Way has captivated the human imagination for centuries. From its mesmerizing spiral arms to its hidden mysteries, we'll be delving deep into the heart of our galactic home. Whether you're a seasoned stargazer or just starting to gaze upwards, get ready to unravel the secrets of our cosmic neighborhood. In this video, we'll journey through the Milky Way's remarkable structure, uncover its billions of stars, and discuss its place in the vast cosmic tapestry. But that's not all. We'll also touch upon the latest scientific discoveries, mind-bending theories, and the cutting-edge technology that has enabled us to peer into the depths of our galaxy like never before. So, whether you're watching from the comfort of your living room or joining us under a blanket of stars, sit back, relax, and prepare to be enlightened by the wonders of the Milky Way. Don't forget to smash that like button, subscribe to our channel, and hit the notification bell so you never miss a chance to explore the cosmos with us. Now, let's embark on this celestial adventure together. The Milky Way is the galaxy that contains our solar system. Its name comes from the appearance it has from Earth, a hazy band of light in the night sky, formed by countless stars that can't be distinguished individually. This name comes from the Latin term Via Lactea and the Greek Galactikos Kyklos, both meaning Milky Circle. Galileo Galilei was the first to see individual stars in this band with a telescope in 1610. Before the 1920s, it was believed that all stars in the universe were part of the Milky Way. The Milky Way is a barred spiral galaxy, with an estimated diameter of about 87,400 light-years and a thickness of around 1,000 light-years at the spiral arms. Recent simulations suggest a potential dark matter area extending up to almost 2 million light-years in diameter. The galaxy is part of the Local Group, which is within the Virgo supercluster, itself a part of the Laniakea supercluster. Containing an estimated 100 to 400 billion stars and a similar number of planets, the solar system is located about 27,000 light-years from the galactic center, on the inner edge of the Orion Arm, a spiral concentration of gas and dust. The innermost 10,000 light-years of stars form a bulge with one or more bars radiating from it. At the heart of the galaxy lies Sagittarius A star, a supermassive black hole of around 4.1 million solar masses. Stars and gases at various distances from the galactic center orbit at approximately 220 kilometers per second. This consistent rotational speed contradicts normal dynamics, implying that much of the Milky Way's mass, around 90%, is invisible and termed dark matter. The Milky Way itself moves at about 600 kilometers per second relative to extragalactic frames of reference. Its oldest stars are nearly as ancient as the universe and likely formed soon after the Big Bang's dark ages. The Milky Way is visible as a wide, hazy band of white light spanning about 30 degrees across the night sky. This band is the accumulation of unresolved stars and matter located in the direction of the galactic plane. The brighter areas within the band appear as soft visual patches known as star clouds, with the large Sagittarius star cloud being one of the most prominent. However, there are dark regions within the band, such as the Great Rift and the Coalsack, where interstellar dust blocks light from distant stars. Various cultures, including the Inca and Australian Aborigines, recognize these dark regions as constellations formed by dark clouds. The visibility of the Milky Way is affected by factors like light pollution and moonlight. It requires a relatively dark sky, with a magnitude of about plus 5.1 or better, to be visible, showing intricate details at plus 6.1. Unfortunately, over one-third of Earth's population cannot see the Milky Way due to light pollution. From Earth's perspective, the visible region of the Milky Way's galactic plane encompasses 30 constellations. The brightest part, the galactic center, lies in Sagittarius, and the band of light appears to pass around the sky to the galactic anticenter in Auriga, dividing the sky into roughly equal hemispheres. The galactic plane is inclined about 60 degrees to the ecliptic, Earth's orbital plane. It reaches as far north as the constellation Cassiopeia and as far south as Crux, reflecting the inclination of Earth's equatorial and ecliptic planes relative to the galactic plane. This results in varying heights of the Milky Way arch in the night sky depending on the observer's location and time of year. For those within latitudes around 65 degrees north to 65 degrees south, the Milky Way can pass directly overhead twice a day. Over the course of history, our perception and understanding of the Milky Way galaxy have evolved through the contributions of various philosophers, astronomers, and thinkers. Ancient philosophers such as Anaxagoras and Democritus speculated that the Milky Way was the glow of stars hidden by Earth's shadow. Aristotle proposed that it existed in Earth's upper atmosphere, with its milky appearance attributed to atmospheric effects. In later centuries, Al-Biruni described it as a collection of nebulous star fragments, while Avempes believed it to be a continuous image in Earth's atmosphere. Galileo Galilei's telescope observations in 1610 revealed that the Milky Way consisted of numerous faint stars. He also suggested that the Milky Way's appearance was influenced by atmospheric refraction. Immanuel Kant, drawing on the work of Thomas Wright, proposed in 1755 that the Milky Way might be a rotating assembly of stars held together by gravity, a concept that later gained support. William Herschel's star counts in 1785 led to a diagram of the Milky Way's shape, with the solar system near its center. Lord Rosse's advanced telescope allowed him to distinguish between various nebulae shapes, lending credence to Kant's idea. Jacobus Kapteyn's study of star motions in 1904 hinted at the galaxy's rotation, revealing two opposing streams of stars. The great debate in the early 20th century involved Heber Curtis and Harlow Shapley discussing the nature of the Milky Way and other galaxies. Curtis's observations of novae within the Andromeda Nebula supported the idea of island universes. Edwin Hubble's breakthroughs in the 1920s, facilitated by the Mount Wilson Observatory's telescope, provided photographic evidence of individual stars within nebulae. He identified Cepheid variables as distance indicators, confirming that the Andromeda Nebula was a separate galaxy, fundamentally changing our understanding of the universe. From ancient speculations to the groundbreaking work of Galileo, Kant, Herschel, Curtis, and Hubble, our knowledge of the Milky Way's true nature as a galaxy among countless others has undergone a remarkable transformation. Over time, our understanding of the Milky Way has been greatly enhanced by various advancements in astronomy and space exploration. The European Space Agency's Gaia spacecraft, launched in recent years, has brought about a significant transformation. Gaia measures the parallax of stars, enabling accurate distance estimates for over 1 billion stars. This spacecraft has mapped the Milky Way in unprecedented detail, with map releases in 2016, 2018, 2021, and 2024. The expansion in observational data has been astonishing, increasing from a few million stars in the 1990s to over 2 billion, while precision and measurable space volume have expanded immensely. The Sun's position within the galaxy is a key aspect. It resides near the inner edge of the Orion Arm, situated within the local bubble. The distance from the galactic center is about 27,000 light-years, and the Sun currently holds an elevation of 5 to 30 parsecs above the central plane of the Milky Way. Understanding the distribution of stars around us is also crucial. In a sphere with a radius of 15 parsecs from the Sun, there exist approximately 208 stars brighter than magnitude 8.5. This translates to a density of around 1 star for every 69 cubic parsecs. Conversely, within 5 parsecs of the Sun, there are 64 known stars, yielding a density of approximately 1 star for every 8.2 cubic parsecs. The Sun's movement and orbit offer additional insights. Its direction of motion is toward the star Vega in the Hercules constellation, forming an angle of roughly 60 degrees with respect to the galactic center. The Sun's orbit around the Milky Way is envisioned as an elliptical path, influenced by the gravitational forces exerted by spiral arms and varying mass distributions. Additionally, the Sun traverses the galactic plane around 2.7 times per orbit. The orbital period of the solar system provides an intriguing perspective. It takes approximately 240 million years for the Sun to complete one orbit around the Milky Way. This lengthy timeframe indicates that the Sun has completed numerous orbits during its existence, totaling around 18 to 20. Velocity and direction also play significant roles. the Solar System's velocity in its orbital path around the galactic center is roughly 220 kilometers per second, 490,000 miles per hour, a mere 0.073% of the speed of light. As the Sun moves through the heliosphere, its speed reaches around 84,000 kilometers per hour, 52,000 miles per hour. Such velocities lead to intriguing consequences. For example, it takes nearly 1,400 years for the Solar System to traverse a distance of 1 light-year, or just 8 days to cover 1 astronomical unit. Additionally, the concept of galactic quadrants helps us visualize the Milky Way's layout. These quadrants are defined by the galactic coordinate system, with the Sun serving as the reference point. Each quadrant is characterized by a specific range of galactic longitudes relative to the galactic center, offering a helpful framework for astronomical navigation and understanding. Overall, from Gaia's revolutionary contributions to detailed insights about the Sun's position, movement, and the structure of the Milky Way, these advancements provide a deeper comprehension of our galactic surroundings. The Milky Way, one of the largest galaxies in the local group, shares its prominence with the Andromeda Galaxy. However, determining its exact size remains a challenge. The majority of stars in the galaxy are thought to lie within a diameter of about 80,000 light-years. The number of stars beyond this region decreases dramatically, indicating an exponential decline in star density. Different methods are employed to define a galaxy's size, yielding varying outcomes. Comparing Cepheid variable stars in other galaxies to those in the Milky Way, an estimate in 1997 suggested an isophoral diameter of about 87,400 light-years. This diameter is smaller than that of the Andromeda Galaxy, and a study in 2015 proposed the presence of a triangulum Andromeda ring with a diameter of 160,000 light-years. Estimates of the Milky Way's mass also vary, with the total mass ranging from 890 billion to 1.54 trillion times that of the Sun. The majority of this mass is attributed to dark matter, which interacts gravitationally with ordinary matter. The Milky Way stellar disk is approximately up to 4,000 light-years thick. Within the Milky Way reside between 100 and 400 billion stars, and potentially as many planets. The exact number depends on factors like the detection of low-mass stars and planets. The Milky Way contains a diverse range of objects, from white dwarfs and neutron stars to interstellar gas and dust. The number of stars decreases with distance from the center, and the disk of stars transitions into a spherical galactic halo that includes globular clusters. The presence of planets and exoplanets, including those within the habitable zone, has been a subject of interest and study. Recent estimates suggest that there could be over 300 million habitable exoplanets in the Milky Way galaxy. The Milky Way is characterized by a bar-shaped core region encircled by a warped disk containing gas, dust, and stars. Its mass distribution resembles the type SBC in the Hubble classification, indicating a loosely wound spiral galaxy. In the 1960s, astronomers proposed that the Milky Way is a barred spiral galaxy, an idea later confirmed by observations from the Spitzer Space Telescope in 2005. The galactic center, located about 25,000 to 28,000 light-years from the Sun, features an intense radio source named Sagittarius A star. It is believed to harbor a supermassive black hole with a mass of around 4.1 to 4.5 million times that of the Sun. This harbor a supermassive black hole is responsible for the motion of material around it, and its accretion rate suggests an inactive galactic nucleus. Debate surrounds the nature of the Milky Way's bar, including its size and orientation. Some suggest the presence of 2 distinct bars, while others propose a single bar surrounded by a ring known as the 5 kiloparsecs ring. Gamma-ray observations have detected emissions from positron-electron annihilations in the galactic center, indicating the presence of low-mass X-ray binaries. In 2010, 2 enormous spherical bubbles emitting high-energy gamma rays were detected above and below the galactic core, attributed to a magnetized outflow driven by star formation in the central region. In 2015, an X-ray flare 400 times brighter than usual was observed from Sagittarius A star, possibly caused by interactions within gas flowing into the black hole or the disintegration of an asteroid. The Milky Way structure includes a bar-shaped core surrounded by a warped disk of gas, dust, and stars. The organization of stars and interstellar medium in the disk forms 4 spiral arms. Spiral arms are regions with higher densities of gas, dust, and star formation compared to the rest of the galaxy. The exact nature of the Milky Way spiral arms is not fully understood. The arms are not perfect logarithmic spirals and can branch, merge, and exhibit irregularities. The Sun is located within one of these spiral arms called the Orion Cygnus arm. There are thought to be four major spiral arms: the near 3 kiloparsecs arm, the Norma and outer arm, the far 3 kiloparsecs arm, and the Carina Sagittarius arm. Additionally, there is the Orion Cygnus arm, where the Sun is situated. The spiral structure of the Milky Way's arms is subject to ongoing debate. The Scutum Centaurus arm and the Carina Sagittarius arm have been suggested as major arms, but recent surveys show that the Scutum Centaurus arm contains more red giants than expected, while the Carina Sagittarius arm does not exhibit the same overabundance. This suggests that the Milky Way has two major stellar arms, while gas and young stars trace four spiral arms. In addition to the major arms, there are smaller structures, such as the near and far 3 kiloparsecs arms. These arms were discovered through radio measurements of atomic hydrogen and are located at varying distances from the galactic center. The overall structure of the Milky Way, including its spiral arms and other features, is complex and has been shaped by interactions with other galaxies and internal dynamics. The Milky Way structure includes a spheroidal halo of old stars and globular clusters. About 90% of these clusters lie within 100,000 light-years of the galactic center, with a few extending farther, such as PAL 4 and AM1 at over 200,000 light-years. Some clusters move in the opposite direction of the Milky Way's rotation, and they can follow rosette orbits. Active star formation primarily occurs in the galactic disk, especially in the spiral arms. The halo, on the other hand, lacks cool gas for star formation. Open clusters are concentrated in the disk, contributing to the overall structure of the galaxy. Recent discoveries have enhanced our understanding of the Milky Way structure. The extension of the Andromeda Galaxy's disk suggests that the Milky Way's disk might also extend farther than previously thought. Evidence of extensions in the Cygnus arm and the Scutum Centaurus arm further supports this idea. The interactions with other galaxies, like the Sagittarius dwarf elliptical galaxy and the Canis major dwarf galaxy, have shaped the Milky Way structure. The Sloan Digital Sky Survey revealed a diffuse structure within the Milky Way that might be a result of a merging dwarf galaxy named the Virgo stellar stream. In addition to the stellar halo, there's evidence of a gaseous halo with a significant amount of hot gas. This halo extends much farther than the stellar halo and could potentially account for the missing baryonic matter in the universe. The rotation of stars and gas in the Milky Way's disk is differential, meaning their rotation period varies with location. The rotation curve, which shows the orbital speed of objects at different distances from the center, indicates the presence of dark matter, as the observed curve doesn't match expectations based solely on visible matter. This suggests that dark matter plays a crucial role in the dynamics of the Milky Way. The Milky Way began as small overdensities in the universe's mass distribution shortly after the Big Bang, around 13.61 billion years ago. Some of these overdensities became the seeds of globular clusters where the oldest stars in the Milky Way formed. Roughly half of the matter in the Milky Way may have originated from other galaxies. Over time, the Milky Way's mass grew through galaxy mergers and accretion of gas from the galactic halo. As the Milky Way's mass increased, it started spinning quickly, causing the gaseous interstellar medium to collapse from a spheroidal shape into a disk. This led to the formation of later generations of stars in the spiral disk. Active star formation primarily occurs in the disk's spiral arms, while the halo lacks the necessary cool gas for new star formation. The Milky Way has undergone mergers and accretion, and it is currently accreting material from small galaxies such as the Magellanic Clouds. Properties of its outer regions suggest that there have been no major mergers with large galaxies in the last 10 billion years, making its history somewhat unique among similar spiral galaxies. The Milky Way and the Andromeda Galaxy are in the Green Valley, a region where galaxies transition from actively forming stars to ceasing star formation. While star formation is slowing down, the Milky Way remains one of the brightest spiral galaxies still forming new stars. The ages of globular clusters provide a lower limit on the Milky Way's age. The Milky Way's growth, structure, and age have been determined through observations of stars, clusters, and galaxies, shedding light on its formation and evolution over billions of years. The Milky Way and the Andromeda Galaxy are part of a binary system of giant spiral galaxies within the Local Group, a collection of about 50 closely bound galaxies. The Local Group is surrounded by a local void, and the Local Group itself is a component of the larger Virgo supercluster. This supercluster is situated within a larger cosmic structure called Laniakea, which includes filamentous structures and voids. The Virgo supercluster is drawn towards the Great Attractor, forming part of this intricate network. Within the Local Group, the Milky Way has several satellite galaxies, including the large and small Magellanic Clouds, which have influenced the Milky Way structure. The satellite galaxies' motions have created a warp in the Milky Way's disk, and they are also believed to be part of a large disk, despite predictions of more random distributions. The Andromeda Galaxy is approaching the Milky Way at a speed of 100 to 140 kilometers per second, 220,000 to 310,000 miles per hour. A collision between the two galaxies is expected in around 4.3 billion years, resulting in the formation of a single elliptical galaxy or a large disk galaxy over the course of about 6 billion years. In terms of velocity, the Milky Way has a peculiar velocity relative to the Hubble flow, the expansion of space between galaxy clusters. Its motion is approximately 630 kilometers per second, 1,400,000 miles per hour, with respect to this frame of reference. The Milky Way is also moving at 552 kilometers per second, 1,235,000 miles per hour, relative to the cosmic microwave background reference frame, which results in a dipole contribution to the cosmic microwave background due to the Doppler shift effect. Thank you for joining me in this exploration of the incredible Milky Way galaxy. From its mesmerizing spiral arms and central bar to its complex structure and interactions with neighboring galaxies, the Milky Way never ceases to amaze. As we've delved into its history, composition, and dynamic features, I hope you've gained a deeper appreciation for the vastness and complexity of our cosmic home. Remember, every point of light you see in the night sky could be a distant star within our Milky Way, and there's so much more to discover beyond what we've covered today. The mysteries of dark matter, the ongoing dance of galaxies, and the future collision with the Andromeda Galaxy await further exploration and understanding. If you found this journey through our galaxy fascinating, don't hesitate to hit that like button and subscribe for more captivating content about the wonders of the universe. Feel free to leave your thoughts, questions, and suggestions in the comments section below. This is Saibot GPT, signing off, and remember, the sky is not the limit, it is only the beginning.